In this video, I want to talk about how neuron-graded potentials are created and why they decay with both time and distance. So I've again drawn a neuron with the soma in red, and I've blown up an axon in green, and I've blown up two large dendrites in blue. And here's our graph looking at the membrane potential on the y-axis, and I put in a few values in millivolts, -50, -60, and -70, and we'll have time on the x-axis. So now recall that a resting neuron without inputs has a layer of positively charged ions on the outside of the membrane and a layer of negatively charged ions on the inside of the membrane, and that the strength of that charge separation without inputs may vary between neurons, but it's often around -60 millivolts for the resting potential. And recall that neurons have a threshold potential that's often around -50 millivolts, so that if the membrane potential at the trigger zone passes the threshold potential, an action potential may be fired down the axon. And recall that with inputs, the resting potential of neurons may be moved by small, brief potential changes that we call graded potentials that may move the membrane potential closer to zero, which we call a depolarization or an excitatory potential, or which may move the membrane potential away from zero and farther away from threshold, which we call a hyperpolarization or an inhibitory potential. Now, to understand how these graded potentials occur, I need to introduce a new type of ion channel, which I've drawn here, and these are neurotransmitter receptors. Neurotransmitter receptors are found at synapses, where the axon terminal of another neuron, where neurotransmitter molecules are released into the synapse, and they bind to these neurotransmitter receptors. Many neurotransmitter receptors are a type of ligand-gated ion channel, which means that unlike the leak channels that we talked about before, which are always open, these channels are gated. They're closed most of the time until their ligand, which in this case is a neurotransmitter, binds to the receptor. And then the ion channel opens and ions may pass across the membrane through the channel. The graded potentials that are produced depends on which types of ions are allowed to pass, because some of these allow only one type of ion to pass, while others allow multiple types of ions to pass. It also depends on how many channels are opened, which depends on the amount of neurotransmitter released into the synapse, and it depends on how long the channels stay open, which depends on how long neurotransmitter stays in the synapse to continue binding to the neurotransmitter receptor. If a channel opens that is selective for only one type of ion, the membrane permeability for that ion is increased, which causes the potential of the membrane around the channel to move toward the equilibrium potential of that ion. And recall that an equilibrium potential is the membrane potential at which a certain ion will have balanced electrical and diffusion forces, so that even if there are open channels, there is no net movement of that ion. If the channel is a sodium channel or a calcium channel, opening of that channel will usually cause a depolarization, an excitatory potential, because these cations will usually flow into the neuron, bringing positive charges into the negative inside of the neuron, causing a depolarization. Because for sodium and calcium, both their electrical force and their diffusion force are trying to drive them into the neuron if there are open channels through which they can pass. Hyperpolarization usually occurs if a chloride channel is opened, because for most neurons, chloride will flow into the neuron through an open channel, bringing negative charges into the already negative inside of the cell, causing the membrane potential to become more negative. And that's because for most neurons, chloride has a larger diffusion force driving it into the neuron against its smaller electrical force that's trying to drive it out of the neuron. Hyperpolarization may also occur if a potassium channel opens, because for potassium ions, its larger diffusion force will usually drive it out of a neuron against its smaller electrical force trying to drive it into the neuron. Let's look at one of these channels a little bit more closely and see what's happening to the ions when neurotransmitter binds to the receptor and the channel opens to the ion. Let's first consider a sodium channel. So let's say this neurotransmitter ion channel, when neurotransmitter binds, it opens and it only allows sodium ions to flow into the neuron. Now, as these sodium ions are flowing through this open channel, there will be an increased concentration of sodium in a small area right around the channel. And as these positive charges are building up on the inside of the membrane around the channel, that's depolarizing this part of the membrane. So let me actually write that. So this piece of the membrane then, what we're going to see is that the membrane potential starts to move to a less negative value. But then the question is, why does this stop? Why doesn't the membrane potential just keep climbing from here? Well, the first thing that happens is that the neurotransmitter will leave the receptor. It will become unbound to the receptor, and without neurotransmitter bound, the ion channel will close. So it's no longer allowing positively charged sodium ions to flow into the neuron. So that's going to cause the graded potential to kind of plateau. It's going to stop growing at that point. But then why does it decay? Why do these graded potentials only last a short time and decay with time? Well, the reason for this is that this little area right here where there's a high concentration of sodium ions isn't going to stay like that, because all of these sodium ions are acted on by electrical and diffusion forces inside the cytoplasm, just like they are when we're talking about them across the membrane. The diffusion force is going to want them to go from areas of high concentration to areas of lower concentration. And the electrical force is also going to want that. These positively charged ions are going to want to get as far away from each other as they can, because like charges repel each other. So these sodium ions that came in through the open channel are going to go racing off in every direction to get as far away from each other as they can, and they'll just mix in with all the other ions through the cytoplasm until they are as far away from each other as they can, and then they're in equilibrium. And the cytoplasm has an enormous total number of sodium ions compared to the very small number that came through this open channel during the brief time that it was open. So because this small area of increased concentration of sodium ions isn't going to last, all these sodium ions are going to race away from each other, the depolarization of this piece of the membrane is not going to last either. And this is going to be the decay that happens with time. That piece of membrane is just going to go right back to the resting potential once all these sodium ions spread out and equilibrate through the rest of the cytoplasm. Imagine this as a small hemisphere of increased sodium concentration on the inside of the membrane centered on the open channel. This hemisphere rapidly expands in all directions away from the channel on the inside of the membrane, weakening as it expands and as these sodium ions are getting farther away from each other, until it eventually fades away entirely as the sodium equilibrates with the sodium in the rest of the cytoplasm. As this little hemisphere of increased sodium ion concentration expands away from the channel, weakening as it expands, a wave of depolarization starts spreading across the membrane away from the open channel. And that wave of depolarization is also weakening as it spreads. So that right here, it might be a certain size. If we look at this piece of membrane, maybe it's about that size. But as it's kind of spreading across the membrane, if we check in with it a little farther away, it has weakened. It has decayed. And as it continues spreading along the membrane and these sodium ions are spreading farther and farther apart, the depolarization gets smaller and smaller, so that the graded potential degrades with distance, just like it degrades with time. So this is the way that graded potentials degrade with time and degrade with distance, so that their effects are only additive if they occur close enough together in time and in space. The most common cause of an excitatory graded potential in neurons is entry of sodium ions through neurotransmitter receptors that allow sodium ions to pass when the neurotransmitter is bound. But the mechanism would be the same for calcium ions. They also would flow into the neuron, bringing their positive charges in, which would then rapidly spread out in every direction, causing an excitatory potential. The most common cause of inhibitory potentials in neurons is entry of chloride ions through neurotransmitter receptors that allow chloride ions to pass. And the mechanism is really the same, but because chloride is an anion, we're going to have a little buildup of negative charges affecting the membrane potential around the channel, making it more negative. And then the diffusion forces and the electrical forces will cause the chloride ions to spread out to try to equilibrate in the rest of the cytoplasm, so that a hyperpolarization caused by chloride ion entry through a neurotransmitter receptor will also decay with time and with distance. Inhibitory potentials may also occur if a neurotransmitter receptor allows potassium ions to exit the neuron. The mechanism of this is really the same as well, but now we have a collection of positive charges around the open channel on the outside of the membrane. So that makes the positive outside even more positive, which is the same thing as saying that the inside of the membrane is more negative, so you get a hyperpolarization. And then this little area of increased potassium ion concentration will rapidly dissipate out, but in this case it's dissipating into the interstitial fluid outside of the neuron as opposed to the cytoplasm inside the neuron.